Hi guys, this is the second or third video in series for electron configurations and rules for the filling of electrons inside of an atom. So in this video what we're going to do is we're going to go over three principles that govern how electrons fill all of the different orbitals in an atom, and then we'll do a few examples. We'll do some practice. So there are three rules here. And if you've been doing electron configurations, you've already been doing these all along, except we just haven't really given a name to them. So the first principle that we've got is called the off-bow principle, and it's that electrons enter orbitals of lower energy first. So really what that means is we always start at 1s. That's it. Start at 1s. Electrons shouldn't be artificially high in their energy levels. If they do, they're in the excited state. And when we are doing their electron configurations, we should always be drawing them in the grounded state, in the ground state. Pauli's exclusion principle is the second one, and this is really, really bad, but I remember it because back in my day, Pauly D was on Jersey Shore. Yep, I went there, okay? And then he has a new job, which is not being a weirdo on the Jersey Shore anymore. He does the turntables in Las Vegas, which means you guessed it, he spins. Get it? Yep. That's honest to God how I remember it, and it's really pathetic. So, if you want to remember it that way, you can be pathetic with me. An orbital can have two electrons. So he actually has two statements. An orbital, this is the first, an orbital can have two electrons. That's the first one. The other one is that those two electrons need to have opposite spins. So his rule is actually kind of like 2 in 1. Must have two electrons, must have opposite spins. Hund's rule states that when an electron enters an orbital of equal energy, one enters each orbital until there's one electron with the same spin, and then they're forced to pair up. So if you remember, when we were discussing the shape of the p orbitals, there's a px, a py, and a pz. Let's see if I can draw those. Here's a px, here's a py, and then z is really the hardest to draw, but it's kind of like that, right? And then it kind of goes in the back. So what Hund is trying to say, and I'll show it in green, is that electrons are going to go one in each. What happens is there's going to be one there, so there'll be a 1 in px, 1 in py, 1 in pz, and they only double up if they have to. That's because electrons are negative and they don't want to be near each other. 1, 2, 3. 1, 2, 3. And now you have a completely filled p suborbital. All right, so let's look at a few examples of each of these in action. On this slide, I wanted to show you the off-bow principle. And I think the boxes might be a little small, so I might blow this up. It says electrons must enter orbitals of lower energy first. So what I'm going to do is I'm going to make this much bigger so that I can draw on it for you. All right. Basically, all off-bow is saying is that we need to start way down here. We need to start closest to, remember this is my nucleus, closest to the nucleus first, least amount of potential energy. Atoms are naturally going to fall towards their most stable state, and that's where it is. So if I start adding electrons here, and in orbital diagrams, we're going to use electrons that look like half of an arrow. So for example, that is an electron with an upspin. And this is an example of an electron with a down spin. So if I add one here, I'll add the second here. Let me show you a violation of the off-bow principle. So I'll add to 2s next, and then I'll do 2p. Now watch how I fill it. 1, 2, 3, 4, 5. And now what I'm going to do is I am going to break the rules. Instead of adding the 6th in P, I'm going to put it up there in 3s. That electron right there is too high. It should have filled the 2p first. So what does that mean about this electron configuration? It's in the excited state. I can tell because there's one electron that's way higher than it should be. Should it be present? Yes, it should. Is it in a region where it can be present? Yes, it is. There's 3 S's all the way up. However, it should have gone back there next to his other 2pz friend. So I can tell this is in the excited state. That's what the off-bow principle looks like, is starting at 1s. If it's violated, you're going to have an electron that's artificially high. So now let's look at Pauli. All right, if you remember, Pauli has 2 rules. He says 2 electrons per orbital. It's too hard to write on this thing. I'm just going to write that. And then the other thing is he's a spin guy. Remember, he's a DJ. So he says when electrons pair up, one must have an upspin and one must have a downspin. And by convention in chemistry, we usually write the upspin first. So let's do an example here where we observe Pauli's exclusion principle. There's 1s. Look, I've got a pair in there. They have opposite spins. Perfect. 2s. Now let's try to do some violations here. 2p. All right. Spot the violation. All right. So what happened was these 2 electrons right here are sitting there with 2 upspins. All right. That is not okay. They need to be spinning away from each other. They are negatively charged. As an example, here's 2 balls. Pretend they each have a negative charge. If they're going to roll away from each other, watch which direction they roll. That one goes that way, and that one goes that way. See how one is rolling to the left and one is rolling to the right, and they're opposite? We just show that in chemistry as an upspin and a downspin. So these can't be both rolling the same way, or else they're kind of like headed in the same direction, right? So that's one violation that you might see with the Pauli exclusion principle. The other one, and that's the 2-spin one. The other one might look something like this, if I have an up, a down, and an up. Why is that a violation? Well, all 3 of those are existing in the same orbital. And if you look, it says that right there, an orbital can only hold 2 electrons at a time. It cannot hold 3. The space is not defined for 3. That is not okay. All right? So that's a Pauli exclusion principle. Last one is Hund's rule. Hund's rule is probably the most, I was going to say, if there's probably an error made most often, it's probably a violation of Hund's rule. So Hund's rule kind of kicks in, not necessarily with the s orbital. So s is really easy to fill, right? You just get 2. But with p. So, for example, if I have something like carbon, which is 2s2, 2p2, a lot of students will draw this. Ta-da! That is not correct. What we need to do is we need to separate these electrons. You got to remember, they're negative. They don't want to be near each other, right? So if you get into the habit of filling your electrons, 1 in each box every time you go over. So 1 here, 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 then go back and finish when you need to. This is going to come out much nicer, and you're not going to make that kind of error with Hund's rule. So let me just show you. I'll finish filling this 2p, downspin, downspin, downspin. 3s, 2, 3p. Again, I go 1, 2, 3, then go back and fill 4, 5, 6. All right. So just be really careful with Hund's rule. Put 1 in each region of space until you go back and you have to fill them. All right. So here are some examples. I think I've got magnesium and sulfur on here. And so if I look, Magnesium is 1s2, 2s2, 2p6, 3s2, and then we are all done. All these orbitals do, these orbital pictures, these orbital diagrams do, is they take our electron configuration and they make a picture out of it. So this 1s2 is going to be reflected in my orbital diagram as just this, an up and a down spin. Done. 2s2, that means I put 2, 1 up, 1 down. 2p6, put 1 in each, satisfy Hund's rule. Now go back and double. There's my 2p6. So check, check, check. 3s2, an up spin and a down spin. There you go. So that's what magnesium looks like on its ground state. Now, if I wanted to, I could draw this in excited state. So what I'm going to do is I just deleted one of those 3s electrons, and what I'm going to do is I'm going to take it and I'm going to throw it way up. See it up there, up in 5s? I can tell that this is a possible electron configuration because 5s does exist. It is a region of space that's available to that electron, and it's just way higher than it needs to be. And if this electron were to fall back down, it would live in the 3s with its other pair, and it would be ground state magnesium. All right? If I was going to give you an example of something that does not exist, what I would do is I would say, let's see, let me delete that. We're not going to do magnesium anymore, especially because I don't want to keep track of how many electrons I have. But let me draw here. I'm going to draw another box, 2p, like a pretend box. And this will be, I'm not going to have enough room. 1, 2, 3. Oh, yeah, I do. 1, 2, 3, 4, 5. 5 boxes for 5 orbitals. And we're going to call this 2D. First thing you got to ask yourself is, does 2D exist? Answer, no, it does not. That region of space is not available for electrons because we basically add a region of space for every energy level. So the first energy level has 1 region, second has 2, third has 3, 4 has 4, fifth has 5, 6 has 6, etc., etc. So if I was going to show you this like really funkalicious, right, electron configuration where I've got 1 rogue electron in this 2D orbital, this doesn't even make any sense. There's no such thing as 2D. This doesn't happen. This is flat out not a consideration, right? However, like I said, the difference between that and then something a little weird, kind of like electrons at a higher energy level. So if I take my 1 and put it back in 3s and then arbitrarily just kind of like promote another one to 5s, that's a possible electron configuration. Right now, as it stands, it's violating the off-bow principle, but if I drop it back down, it would be back down in its ground state. So we're good. So there's lots of kind of weird things we can kind of model with types of diagrams. Here's sulfur. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So I'm going to show that. 1s2, 2s2, 2p6, and I always do 1 in each, right? 3s2, and then 3p4. So I'm going to go 1 in each, 2, 3, and then it has a pair here. So if you look, you've actually got these 2 lone electrons here, 1 and 1, kind of hanging out by themselves in their p, y, and pz regions. This one is the only one that's paired because it had to. That's Hund's rule. Now, the S ion can generally be sulfur with a -2 charge. So it's really easy to see with a diagram like this where those extra electrons are going to add to. They could add to 4s, but that would be a violation of the off-bow principle, and this is not in the excited state, mostly because they don't tell me that. So anytime I add electrons, I want to add right to the outside here in these valence electron spaces. So if this is going to be, I'll do them in green, if this is going to be the sulfide ion, which is sulfur with a -2 charge, I would add those two electrons right there. Now it's an ion. Now it is isoelectronic. That means isoelectronic, same electron configuration as a noble gas, which is the whole point, right? They create ions to be more stable versions, to lower their potential energy. So it makes sense that ions are isoelectronic to a noble gas. All right? I hope this was helpful, and I will see you on my next project.